Hello everyone! In this video, the star Sirius is going to replace the Sun in our solar system. You'll get to see and find out what happens in the end. There will be a few different versions of the experiment, all using the Universe Sandbox simulator. Let's get started. And the first experiment will be about what happens if the star Sirius suddenly, just like that, instantly replaces the Sun in the solar system. To do that, I'll select Sirius and use it to replace the Sun. Before we start the simulation and see what happens, let's compare the star Sirius with our star the Sun. Here, as you can see, the star Sirius is on the left and the Sun is on the right. That's the difference in size between them. And to be more specific, the mass of Sirius is twice that of the Sun, and its radius is 71% larger than the Sun's. The average temperature of Sirius is 9,689 degrees Celsius, and it has a luminosity of almost 26 suns. Let's also take a look at the habitable zone of this star. With Sirius, Mercury and Venus are in what's basically the black zone, which means it's incredibly unbelievably hot. Earth and Mars are in the red zone. The asteroids in the main belt are also in the red zone, and only Jupiter's orbit ends up in the green zone, where the temperature could be normal. And Saturn then is the first planet to enter the blue zone, where it's a bit colder. As for the other planets, well, you get the idea. And now I'm starting the simulation, and let's see how the orbits change. Whoa, look how Mercury's orbit changed, and you can see that burning tail, which means Mercury heated up instantly. The orbits are changing because the star's mass, as we saw, is twice that of the Sun. That's why the orbits are thrown off and become more elliptical. The same thing is happening with Mars and the asteroids, and the same will happen with the gas planets. I'll speed up time. Almost a year is passing per second, and as we can see, yes, Saturn, Jupiter, Uranus and Neptune, all the objects will change their orbits, becoming more elliptical. The star's mass increased sharply, so it pulled everything closer, and that's what caused the orbits to change. Even from a distance, you can clearly see Venus and Mercury burning. Let's take a closer look at how it all appears. Here's Venus. It has this blazing tail. It's losing matter. Its average temperature is over 1,800 degrees Celsius. Incredible. And Mercury looks like this. You can even see a burning Mars in the background. Wow, that's cool. And so on Mercury, the temperature was just over 1,000 degrees. Well, the orbit isn't perfectly circular here, so the temperature varies. And Earth ends up looking like this. Our unrecognizable planet with an average temperature of 673 degrees Celsius. Well, we'll look at the temperatures and all the planets in more detail in the second part of this experiment. And now let's move straight to the second part of this experiment. In the second part, I've again placed Sirius instead of the Sun, and this time the planet's orbits won't be disrupted. They will, roughly speaking, stay in their old places. True, they'll be in perfectly circular orbits, but in principle that won't really affect the essence of the experiment. We'll be able to find out the specific temperature on each planet. So I'm showing you that we have not just the inner planets, but also Jupiter, Saturn, Uranus, Neptune, and even Pluto is included in this system, which contains only the planets. I've also added some interesting moons to Jupiter and Saturn. We'll see what the situation is like for them. And now I'm going to fast forward a few hundred years and find out what the final result will be in this system. I fast forwarded about 250 years. It looks like, as I was watching, the temperature has now stabilized everywhere. And I'll show you the habitable zone one more time. The situation is the same here. Only Jupiter is in the green zone, while everything beyond Saturn falls into the blue zone. Let's start with Mercury. Its average temperature has stabilized at 547 degrees Celsius. And we can see this burning tail. It's actively losing matter. And on the hottest planet in the entire solar system, Venus, the average surface temperature has now stabilized at an astonishing 1,354 degrees Celsius. And we can also clearly see this incredibly scorching tail. Incredible. Meanwhile, on planet Earth, it's 536 degrees Celsius. And this is what it looks like. It's unrecognizable. The dark side, the part turned away from the star, is just glowing with molten rock. And the day side looks like this. If we hide the atmosphere and clouds to get a more detailed look, you can see that the consequences here are just horrifying. At the equator, it turns out the maximum temperature on Earth reaches 650 degrees. That's incredibly harsh. And it's clear that there's no life on Earth anymore. By the way, the distance from Earth to Sirius is almost 1 astronomical unit. For anyone who doesn't believe me, I'm showing you right now. And now the planet Mars. Mars looks interesting. It's acquired an atmosphere and clouds, and it looks something like this. But it's true, it's very hot. The average temperature is 280 degrees. And even at the poles, it's still very hot, 133 degrees Celsius there. I'll hide the atmosphere and clouds from view, and let's take a closer look at the surface. The ice caps it used to have, as we can see, have disappeared. And basically, there's no liquid, nothing. I assume the ice caps melted and formed this atmosphere. And what's the result? The atmospheric pressure on Mars is now basically the same as on Earth. Well, that's not bad. Of course, the life likelihood here is 0%. And now for the most interesting part. Next up is Jupiter, and as we remember, Jupiter is located perfectly in the green habitable zone of the star Sirius, and as we can see, its average temperature is minus 22 degrees Celsius. But that's not the most interesting part. The interesting part is what's happening on its moons, and the closest large moon to Jupiter is of course Io. Its average temperature has stabilized at minus 39 degrees, and even at the equator it's minus 21, so there's no positive value. And Io has acquired an atmosphere, and it looks nothing like it used to. Let's hide the atmosphere and clouds and see what's on the surface. Is that greenery? Is that vegetation, guys? Look, it's all green here. And are those green oceans what? Well, look at that. Closer to the poles, there's something like ice. Let's take a closer look, and look what we've got. The atmosphere on Io is completely formed from sulfur dioxide. And even this liquid that we see is an ocean of sulfur dioxide. This is incredible. There's also ice made of sulfur dioxide. Well, all in all, very interesting. But why is there vegetation here? What, has some kind of exotic life evolved here? Let me check for sure if this is really life. Here, I'm turning off the vegetation view, and yes, as we can see, that is indeed the vegetation. Well, this is incredible, but to be fair, the simulator shows a 0% life likelihood on Io, but there is some vegetation. Maybe it doesn't count exotic life as regular life. Oh well. Next up is Jupiter's second largest moon, Europa. Its average temperature is minus 54 degrees Celsius. So roughly speaking, nothing has changed here. It's still an ice moon, just as it always was. However, the situation is much more interesting and complex on its largest moon, Ganymede. It has an average temperature of 64 degrees Celsius, and as we can see, it's an ocean moon. Let's see, if I hide the atmosphere and clouds, is there any land here? Yes, there's a little bit of land. Well, of course, I don't see any life on these islands. The islands are lifeless. But there's a lot of water, and maybe, after a huge amount of time, some kind of life could have developed. But we see that a very dense and thick atmosphere has indeed formed on this moon. Although the simulator shows that there's a life likelihood of 11.5%. It turns out that on Ganymede, the surface pressure is 0.6 atmospheres. In principle, a more or less normal atmosphere has formed, and the farthest large moon of Jupiter is Callisto. Its average temperature is 194. It turns out it's too hot here. But there's a minimum temperature of minus 40, so at the poles there could be normal conditions. If we hide the atmosphere and clouds, we see that the equator is completely without water. There's no liquid ocean here anymore. But at the pole, as we can see, there's a patch of liquid water like this. Let's see, what's in the southern hemisphere? It looks the same here too. Of course, there's no life here. For some reason, it's hotter here than on Ganymede. The pressure on Callisto is very high, at 21 atmospheres, and it shows there's a tiny life likelihood of less than 1%. Next, let's see what's happening with Saturn and its famous moons. Its average temperature has stabilized at minus 87 degrees Celsius. And let's check its famous moon Enceladus. Its average temperature has stabilized at minus 134 degrees. In principle, its appearance has not changed much. However, it seems like some kind of atmosphere has appeared due to the heating, but this atmosphere turned out to be very, very thin. And on Saturn's largest moon, which is called Titan, the average temperature there is actually very good, just over 16 degrees Celsius, and the maximum temperature doesn't go above 30 degrees. I'll hide the atmosphere and clouds. Let's see what's on the surface. We see a huge ocean. It's flooded almost everything here, right along the equator. And closer to the poles, there are continents, and here they are green, though they are mixed with ice. And this is life itself. There it is, everyone. Life has formed on Titan. You can clearly see it's a living moon. You know, out of all the objects we've looked at, Titan looks like the best candidate for colonization right now. It shows a life likelihood of almost 10%, although I think it was higher on Ganymede, but still, here we can clearly see life. And of course, this dense atmosphere that prevents us from seeing the surface hasn't gone anywhere, and the pressure on Titan's surface has stabilized at just over 1 atmosphere. That's basically the same pressure as on our planet Earth under normal conditions. The next planet in the system is Uranus. The temperature on Uranus has stabilized at minus 145 degrees Celsius. And on the last planet in the solar system, Neptune, the temperature has stabilized at minus 169 degrees Celsius. Of course, let's not forget the dwarf planet Pluto. On Pluto, the average temperature has stabilized at minus 179 degrees Celsius. And it looks quite interesting. It's poorly lit because it's far from the star, but I'll do this and we'll be able to get a good look at it. We can see some kind of dense atmosphere has formed. It's very cold here though. I take it the atmosphere is formed from nitrogen. If we take a closer look, that's exactly right. We can see nitrogen, and there's a lot of it in the atmosphere, and also a little bit of methane. And there's also an ocean of liquid nitrogen. Now that's really cool. I'll hide the atmosphere in clouds, and let's see where this liquid nitrogen is. In principle, Pluto's surface is essentially unchanged from before. However, there should be liquid nitrogen seas or lakes located somewhere. It's quite hard to see them though. There are probably very few of these, and it's not not clear exactly where they are. Maybe in the depths of some crater, I'm not sure. On Pluto, the surface pressure has stabilized at 0.55 atmospheres, and this shows there's no likelihood of life here. And the third part of the experiment will be to carefully place our planet Earth in the habitable zone of the star Sirius at a distance of about 5.05 astronomical units. Bob, I'll place it right here. And this is the orbit Earth ended up with. And now guys, look, this is the ideal distance to achieve about the same temperature on Earth as you would expect in a typical normal solar system. I'll start the timer just so you know we're running at 1 month per second, and if you look at the temperature you'll see that it will basically stay the same as before. And so as you saw, the average temperature rose by about 1 degree. Of course, we had a long winter here, as you could see. As for Earth and the year in general, a year on Earth in this case turns out to be almost 8 Earth years. That's incredible. That is, in 8 years, Earth makes a full orbit around the star Sirius in a place like this where the habitable zone is. So that means 4 years of a cold season and 4 years of a summer season. So winter lasts longer, and this of course will affect the climate on our planet. And well, that's the situation basically. And the year became longer because the distance from the star is also greater. That's why Earth needs more time to orbit the star completely. Well, at the same time, as I can see, the surface pressure isn't changing and the life likelihood remains at a good high level, over 90%. And so this is basically how Earth is illuminated by the star Sirius. Sirius gives it a slightly different color with its glow. I've also landed on the surface of our planet Earth, and let's see how Sirius looks in the sky from Earth. This is what it looks like through the clouds, and this is from space. And so that's the result of the experiment. Please rate it with a like and write what you think about this experiment. Thank you very much for watching, and until the next experiments in the universe.